Hi everybody, this is Mr. Lee. In this video, we're going to go over air resistance. So let's begin. For air resistance, this is a variable force, meaning that the force of the air resistance can change as time moves on. So what we're going to do is we're going to look at multiple parts of a object's journey. So for our derivation, we're just going to imagine an object that is dropped, and there's going to be a force of gravity that pulls it down, and there's going to be a force of air resistance going up. Now, I'm just going to write it as F of AR for air resistance. Sometimes on the AP exam, you'll see it written as F of capital D, which stands for drag. And for the sake of this video, we're going to say that the air resistance is equal to B times V, where V is a velocity. Now, that B is a constant, and that constant comprises of many different things. One of those things is like the surface area that touches the air. Another one is the density of the fluid that the object is traveling through. So you could actually use this formula or these notes if you're doing fluid dynamics, where a object is traveling through water. So the big idea behind this is, yes, even though the air is not a fluid, we can treat it like a fluid, because as the object is passing through air, it pushes away objects. Okay, so there's other stuff that makes up the constant, but this is the two main ones. And just one more time, the surface area is the part that is actually making contact with the air. So the time that we're going to be looking at, so we can imagine that this part of the journey, we'll just call this part T, where T initial is where we first drop the object. So when we first drop the object, we just have F of G pulling it down, and there's no air resistance, because air resistance is B times V. And when you first drop that object, the object's velocity is 0. So there's no air resistance. Now, eventually, we're going to get to a point where we call terminal velocity. So terminal velocity, there's a couple of very important things about terminal velocity. This is where the system is in equilibrium, meaning that the force of air resistance and the force of gravity are equal to each other. Now, more importantly, the acceleration is going to be 0 meters per second squared. Okay. And at this point, the object is neither speeding up nor slowing down. It reached this max velocity. So to show this, we're going to draw it like so, and we're going to create our equilibrium arrows just like that. Okay. And at this point, we're going to say that T is equal to infinity or approaching infinity. So that's a pretty powerful tool in math, especially in calculus, where if you're trying to denote a long period of time passing, we just say that T is equal to infinity. Okay. So there's a couple of things that we want to get to. The first is, how can you create a differential equation to eventually solve for a velocity function? Next one, we're going to try to solve for a velocity function. And the very last thing is, what is the terminal velocity for a falling object given these parameters? Now, we're going to start from the very last thing, and that is the idea of the terminal velocity. Let's get that out of the way so that when we eventually get to the terminal velocity formula, we can double check ourselves. So one of the things that we know is that the acceleration upon terminal velocity is 0. And what this means is that your net force is equal to 0. So if I scroll back up, we see that when we reach terminal velocity, we already have a free body diagram. So in order to create a net force formula, we got to always follow our free body diagram. So here we have BV minus mg. And so we see that BV is equal to mg. So the terminal velocity would be V is equal to mg divided by b. And we got to this point simply by addressing the idea that terminal velocity, your acceleration is equal to 0. Therefore, your net force is equal to 0. And from there, we just did a simple derivation. Okay? So we got to terminal velocity through conceptual knowledge there, and that's very important for you to know. However, I will also want to show you how you can get to it through differential equations. So let's start off with that. We're going to start off with F equals ma. And the free body diagram that we're going to reference is the middle part. Okay, so this could be at any time other than your initial drop and any time that is not infinity. And so if we take a look at that here, we're going to write the rest of the forces. Now we have to be careful here because the object is accelerating downwards. So when this object is accelerating downwards, we're going to say that our acceleration is negative. And the reason why I want to point that out is here, we know Newton's second law is just F equals ma. But if I were to make this a little bit more accurate, we would write this as negative ma is equal to the rest of the formulas. And so we have air resistance pointing up, so that's positive. And then we have force of gravity pointing down, of course, because that's negative. All right, and so from here, I want to get rid of my negatives from my ma. This is going to make our lives a little bit easier. So we get ma is equal to fg minus f of d. All right, so from here, there's a couple of things that we can do, including a substitution. Okay, so the first thing I want to show you is that on the AP exam, if they ask you to create a differential equation, what they're really looking for you to do is to create a substitution for probably one of the kinematic variables, and that will be our A. So we know that A is either going to be d squared x over dt squared or dv over dt. And for the sake of this problem, I want to keep it in terms of dv dt because one of the formulas after our substitutions will have a v in it. And so that's going to be our changing variable. So let's see that. We know that fg is just equal to mg, and we know that fd given by the problem is bv. And there's that v I was talking about. So that is our variable. Now, one more time, what I want to do is I want to point out all of the constants, just to really hone in on the idea that v is our only variable. We know that the object's mass is a constant. We know the acceleration due to gravity is a constant. And I just told you that b is the constant for air resistance. So that leaves us with the only two variables remaining as velocity, and velocity over there. Okay. So if it asks for a differential equation, this is fine, but I'm going to clean it up a little bit so that we just have dv over dt is equal to the remainder. And what that looks like is dv over dt is equal to g minus b over mv. All right, so getting to that point, it's fantastic if you can follow along the mathematical steps there. And from here on out, what I'm going to do is I'm going to take a little a mathematical little trick, a little shortcut, if you will. You see that b over m? That b over m, both of those are constants. And when I'm doing this math here, I don't want to be dealing with anything in the denominator. It just makes things a little bit more messy. So I'm going to assign a constant for that b over m. I'm just going to call that constant the letter k. All right? And so what we get, if I substitute in the constant, dv dt is equal to g minus kv, now becomes our formula. So we create a differential equation. So step 2 is to create a velocity function from this differential equation. So let's do that next. From this differential equation, if we want to create a velocity function, we just have to follow the rules of math. We want to make all of the like terms together. So you see this g minus kv over here. Okay, I'm going to put that in parentheses. I don't want to separate that. And what I'm going to do next is I'm going to divide both sides by g minus kv over onto the other side, for the sole reason that v is over there and we have a v right there. So we want to make the we want to create all of the variable terms together on one side. So we get dv over g minus kv, and that dt I'm going to just shove onto the other side, so that's by itself. All right, so from here we have to take the integral of both sides. But before I do that, in your calculus classes, you learned of a technique called the u substitution, and we're about to do that right here. I'm going to make u is equal to g minus kv, and if I take the derivative of both sides, I get du is equal to negative k dv. And so here what we see is our substitution, where this dv in the numerator here is right there, okay, and that u that we use for the u sub, g minus kv, will be all in the denominator. Okay, so if I do my u sub appropriately, we get the integral of negative 1 over k du over u is equal to the integral of dt. Okay, now notice here I didn't set my bounds just yet, and that'll come in the following step. The bounds on the right-hand side is something that we can actually do ahead of time, where we know that our journey, our time journey, starts off at 0 seconds, okay? And we want to get to a point where we reach terminal velocity. So we can make t infinity, but for the sake of the problem and the sake of reality, we know that objects don't fall for an infinite amount of time. We're just going to call it t final, okay? So we get the bounds over there, and the integral of dt just gives us t, or in this case, t final. I'm just going to leave that f out. Like, just know that the f will be there, but just to save time and space, I'm not going to include that tf. All right, on the left-hand side, always identify your constants. And on the left-hand side, my constant is this -1 of k. And the reason why we want to do that is we want to bring that out so that we get the integral of du over u, like so. Taking the integral of du over u, if you remember your integral rules, simply gives you the natural log of u with the unknown bounds is equal to tf. Now, I do believe that in your math classes, you're supposed to create your bounds with respect to u, but for the sake of this problem, and because this problem is based off a object that is falling, which is like, a real life kind of scenario, what I want to do is I want to substitute back in the u so that I can create our bounds appropriately based off of our scenario. So we get the natural log of g minus kv, absolute value, and now we can think about our bounds. So if you remember, the bounds for the t on the right-hand side, we said that the upper bound was t final and our lower bound was 0. And so the bounds on the left-hand side has to match the bounds on the right-hand side. So the initial velocity, v initial, would be 0 when we first drop it, and we know that the upper bound would be the final velocity, or v terminal, or vt. Okay, and so with those bounds created, now we can finish the whole integral process, and what we get is -1 over k times the natural log of g minus k vt, absolute value, minus the natural log of g, absolute value, is equal to tf. I'm going to close that bracket right there. Okay, so we're almost there. Remember, the end goal of this is to find a velocity function, and that velocity function is hidden right there, that v final, right? So we want to know what that v is. So what I'm going to do is I'm going to somehow extract that v final out according to the rules of math. So we have this pesky -1 over k on the left-hand side. I'm going to multiply both sides by -1 over k. I'm going to do this step by step. So we get g minus kvf. And you see here where we have a negative ln of g, I'm going to use the natural log rules. And whenever you're subtracting the natural log by a natural log, you're just dividing the natural logs, the inner part of the natural logs together. So we get negative k t. So now we have a natural log on the left-hand side, and the only way that we can get rid of that natural log is to raise everything with respect to e. So we get g minus kv over g is equal to e to the negative kt power. Okay, and now what we can do is a little bit more algebraic, where that v is still there, and we want to extract that v. So what I'm going to do is I'm going to multiply both sides by g, and so we get g minus kv is equal to g to the negative kt power, and then I'm going to subtract g from both sides. So we get negative kv is equal to g minus kt minus g, like so. All right. At this point, all we have to do is divide both sides by negative k, and so we get the velocity at any point. Okay, so this is technically v of t at any point is equal to g divided by k over 1 minus, there should be an e there, right? E to the negative kt power. Excuse me, I think I replaced that e with the g, so I'll go back and fix that. Right there and right there. Cool. All right. Okay, so this becomes our velocity function at any time. So if you remember, the two bounds that we discussed was that at t is equal to 0 seconds, our velocity is 0. So if we plug in t for 0 into our velocity function, we should get that same result. So let's see it. We have v is equal to g over k times 1 minus e to the negative kt power. What I'm going to do is I'm going to show you that the negative kt, so whenever you have a negative exponent, it's just the values in the denominator. So when we plug in 0 there, it's e to the 0th power. If you remember your rules of math, e to the 0th power simply gives you 1. And so we get 1 minus 1, which is 0. 0 times g over k gives us 0. So the initial velocity at time 0 is equal to 0 meters per second. Isn't that nifty? All right. Now, what about at time is equal to infinity? We said that at time is equal to infinity, we have our terminal velocity. And as a reminder, if I were to scroll back up, we said our terminal velocity is mg over b. So let's see if that still holds true. Where do we start? All right. So from here, let's have t is equal to infinity. And we know that there it's mg over b. So that should be our final answer, mg over b. Let's take a look. Yes, mg over b. Okay, so we want to make sure that our terminal velocity does in fact equal mg over b. So what I'm going to do is I'm actually going to start from this step here, okay, because that step there will show us our substitution. So we get g over k, 1 minus e to the negative infinity power. So that gives you g over k times 1 minus, and e to the negative infinitieth power gives you 0. So this just gives you g over k. Now, if you remember, the terminal velocity should have been mg over b, and so that mg over b comes from substituting back in that k with b over m. So we do get g m over b, like so. So we do get that terminal velocity that we figured out through conceptual methods from the very, very beginning. All right, so we were able to figure out the velocity function. We were able to create a differential equation, and from there, we were able to prove that your initial velocity is in fact 0, and we were able to show what the terminal velocity is based off of the given information. So the very final thing I want to show you is what the graphs would look like. And let's approach this through conceptual ideas first. Let's start off with a velocity time graph. So with the velocity time graph, we know that the starting velocity will be 0. And for the sake of this graph, we'll just make the direction that is moving positive, right? So it should be negative, but just for the sake of what the graph looks like, we'll make it positive. It's going to go up, and it's going to have a asymptote like so, okay, where this asymptote is our terminal velocity, and we said that our terminal velocity was m over b times g, okay, and your initial velocity here is 0, and because that's where we first released it. The acceleration one, we can use the same ideas, where our starting acceleration, we actually do start off with an acceleration. So if you remember, the free body diagram that we started off was something that looks like this, and so the only acceleration is that g. And once again, we're making that down positive. So this value would be 10 down, and then it flattens out, and we have to make sure it reaches that horizontal asymptote, because as time approaches infinity, we reach terminal velocity, and that's where your acceleration is 0. And the final one, now this one's a little bit trickier, the position versus time one, because we should break up this into 2 parts. The first part, so it starts off at a high height, and is going to have a slow velocity. It's going to speed up, but eventually it's going to get to a point, and I'm going to call this point t of terminal velocity. Okay, so that's the time where the object reaches terminal velocity. And it's important to note that from there, your line is now straight. Okay, so just in case you have a hard time really showing that, I would just write in that your slope, or excuse me, we have constant slope. Okay, or we can write we have constant velocity, right? Because that's where we have terminal velocity. All right, and that is it for air resistance. I'll see you all next time. Bye-bye.